I don't know if you've noticed, but I've had the same clothes on for a long time. It's been a long day. Video after video after video. All right, acid-base equilibria. Very important topic for your AP Chem exam. Great topic in general. I mean, acid-base equilibria. Love it. Love it. The better you understand it, the more you love it. So I hope that this works. It does take practice. Okay, this takes practice. It takes practice. It takes, the more experience and practice, the easier it gets. It was not always easy for me. Now I see why it's intimidating, but man, is it just great. Okay, so we're talking about acid-base equilibria. Let me start that over. Okay, acid-base equilibria. Oops. So this occurs not when we have strong acids, but this is when we have weak acids or bases. All right. And I think the rest of this unit will deal with acid-base equilibria, well, a few other topics. Okay. We have Ka values. We have Kb values. Acid equilibrium constants, base equilibrium constants. Weak acids have Ka values. Weak bases have Kb values. They're in indexes. You can find them. They will most likely be provided to you, right? The lower the Ka, the weaker the acid. Now, it's really cool that the Ka for an acid multiplied by the Kb for a conjugate base is always equal to 1.0 times 10 to the negative 14. So if I have a Ka and need a Kb, I can easily get that value. And if I have a Kb and need a Ka, I can easily get that value. Common Ka must be used in acidic reactions. All right. Kb must be used in basic reactions. All right. Okay. And that is when the base is a reactant, right? And this is when the acid is a reactant. Acid is reactant. I think that will hold true. And base is reactant. That actually is not going to work because there's going to be so many conjugates. So I'm not going to say that. It's more about the H and the OH, okay? Or is an H being taken or is an H being released, okay? So for a conjugate acid-base pair, you can compare the Ka to Kb. If the Ka is stronger, then it will proceed in its acid version. If the Kb is stronger, it will proceed in the basic form. Will take control of the system. Okay. All right. There's also a pKa and a pKb, just as the pH is equal to the negative log of the H, and the pOH is equal to the negative log of the OH. There is a pKa, which is equal to the negative log of the Ka. That's not a concentration, so I'm not going to write it. And there's a pKb, which is equal to the negative log of Kb. Yes, those would add up to make 14 if high, then low, right? Just as the hydrogen ion concentration goes up, the pH goes down. As the Kb goes down, the pKa goes up, vice versa. And if I didn't state it, there's a pKw, right, which is just the negative log of Kw, right? And that would be 14 at 25 degrees Celsius, right? All right. Okay. So let's just get started, guys. And hopefully you'll be cool with this. I think you will. It's when you get those free response questions that this starts freaking you out. All right. Ethanoic acid. I think we've already talked about the fact that we were learned to call that acetic acid, but ethanoic is actually more proper. So it is C2, it's HC2H3O2 is the way we'll choose to look at it. pKa 1. All right. Ethanoic acid has a pKa equals 4.74. Ka equals, oh, well, pKa equals negative log of Ka. Therefore, Ka equals 10 to the negative pKa. All right. So that would be Ka equals 10 to the negative 4.74, 1.82 times 10 to the negative 5, right? Notice we could have predicted that. That's 5, that's greater than 1, so it's a little bit less than 5, and we have 4.74. 2, if propanoic acid has a Ka of 1.38, then what is the pKa equal to? Well, the pKa equals the negative log of the Ka. That's equal to the negative log of 1.38 times 10 to the negative 5th. Make your prediction less than 5. Around 5, but less, right? Okay, so negative 4.8, right? So let's get that. Oh, got it right here. 4.86. pH equals 4.86. I had done all these problems a few years ago, so I just have my answers right here. So I don't have to use my calculator. Okay, 3. The old days when we used paper. Now it'll all be in here, right? Okay, 3. Which is the stronger acid, propanoic or ethanoic? Well, propanoic has a Ka to the negative 5th, and ethanoic has a Ka to the negative 5th. And it looks like ethanoic is a little bit bigger, right? So ethanoic has a slightly higher Ka and therefore dissociates more, okay? All right, 4. Calculate, what is the pH of a 1.00 molar solution of ethanoic acid? And we need to realize that in number 1, the Ka of ethanoic acid was given to us, right? Yeah. And we calculated that to be 1.82 times 10 to the negative 5th. All right. So what we have here, guys, how am I going to teach this? First approach, we have a weak acid, incomplete dissociation, equilibrium problem, right? So you can, nothing is here but the acid, All right, so we can do one of two things. HC2H3O2 yields, or H plus C2H3O2. Your other option is to write it as such. HC2H3O2 in water. I'm going to write H2O, sorry. In water yields C2, I got to put a negative right there. C2H, well, let me do it in the same order, shoot. H3O plus C2H3O2 negative. Notice I forgot that negative down here. It's really important. I would count yours wrong if you forgot that negative. I'd be like, no, that's not right. There's not a negative there. It's negative. I've just incorporated the water and left the water out. So typically, guys, I use the first one. As you see, it's easier on the brain. So if it is an acid reaction, you do not need to incorporate the water as the reactant. If it is a base reaction, we'll see that we will, because we will need that water, all right? All of these will require ice charts. We have 1.00 molar. We have initial is 0. We've got minus x plus x plus x, 1.00 minus x, x, and x. Okay. We have a Ka that is equal to the hydrogen ion concentration times the acetate ion concentration over the acetic acid or the ethanoic acid, whichever you want to call it. Ka is equal to 1.82 times 10 to the negative 5 is equal to x squared, right? X times x is x squared. And then we will put that over 1.00. Once again, this minus x will be negligible. All right, now we're going to do this in a slightly different way here. That's a funky looking arrow, isn't it? Assumed to be negligible. Why? Because of the small Ka value, right? And if in fact it is less than 5% of original amount, so less than 5% of it actually dissociates, then assumption is valid. Okay? It will always be valid. That's how you prove it. But it will be. Otherwise, we're left with like quadratic equations and such, and we're not going there. You will not be expected to go there. All right. So let's just plug in or do our math, right? We essentially have 1.82 times 10 to the negative 5 equals x squared. So you need to square root both sides. And we have, let's see, what I have that right there. 4.266 times 10 to the negative 3rd. And that is equal to, oh yeah, that's equal to x. X is equal to H plus. The pH is equal to the negative log of H plus. Therefore, the pH is equal to the negative log of 4.266 times 10 to the negative 3rd. The pH should be between 2 and 3. And in fact, it is 2.37. Boom. 3 numbers after the decimal in my pH. I don't know, whatever. I'm not worried about it. Okay, was that the last one? And we've got a 5. So I'm going to need to scrunch my work. Oh, no, I can just pull him down. Come on down here. Yeah. Okay, let's see what number 5 has for us. Calculate Ka, 0.1, H, 1.75, 10 to the negative 3. What was 0.1? Ka equals, maybe I can figure out what I have here. This is number 5. All right, go ahead and get started. I've got a 0.100 molar weak acid, so just call it HA, all right? The hydrogen ion concentration is 1.75 times 10 to the negative 3rd, and we need Ka. Okay, all right. Ka, let's see, let's get our equilibrium expression. We know here that Ka equals H over A over HA. Okay, we know that initially we have 0.10000 change minus x plus x plus x equilibrium. Hopefully you're like, this is easy, and it is, right? You take baby steps. And what we have there is Ka, right? We assume to be negligible. I'll try to remember to prove that in a minute. We have Ka equals x squared over 0.100. Oh, no, look, I totally skipped something, right? I know that this H plus is 1.75 times 10 to the negative 3rd. Okay, so this is 1.75 times 10 to the negative 3rd, right? They gained equal amounts. Therefore, this is 1.75 times 10 to the negative 3rd. All right. And if you put in your calculator 0.100 minus 1.75 times 10 to the negative 3rd, you're going to get 0.100. So that again shows how that is negligible. Now we can solve for Ka equals 1.75 times 10 to the negative 3rd squared over 0.100. Therefore, Ka must be equal to 3.06 times 10 to the negative 5. All right. One more. It says Ka equals question mark. We have 0.250 molar of a weak acid, all right, with a pH of 5.11. And we need to, what do we need? And an H plus, oh, okay. I guess that's what it gives us. And from there, we need to know the Ka. All right, HA. So I'm going to use my pH to get my H at equilibrium. I know I had 0.25 of this, 0, 0 minus x plus x plus x. This will be 0.250 because x is going to be so small. In fact, x is the answer to this problem right here, because that's my hydrogen ion concentration. That's going to be 7.762 times 10 to the negative 6th. And that'll be the same for A, because they are 1-to-1 ratio. Nothing was present initially. So I'm just going to write that down there. And we see that Ka equals 7.762 times 10 to the negative 6th squared over 0.250. And in fact, that gives us 2.4 Ka equals 2.41 times 10 to the negative 10th. All right, so let's practice using all those equations. And unfortunately, I would really like to look at some of these. I'm not going to worry about 1 and 2. You can. The answers are posted to Google Classroom. Which is the strongest base, highest Kb. What is the pH of a 0.44 molar solution of ammonia? First of all, it's Kb we're going to need in order to solve this problem. It is 1.78 times 10 to the negative 5th. The next one has an answer that is 3.36. The next one is methyl amine, larger Kb. All right, therefore greater, stronger base. Okay, so we need to look at 4. You need to do this. Okay, you've got to. Ammonia, so we need to know the pH equals what of ammonia? Ammonia is NH3 and it is 0.44 molar. All right, this is where students get confused. Let me clean that up. I look at the screen, that looks weird. Ammonia, let's look at our major species. Got ammonia, and I've got water. Ammonia, they've told me, is acting like a weak base. Man, I also know, sorry, I've been doing this, you guys, literally all day. I've been sitting here talking to this computer. Kb, but I feel like you're there. Kb equals 1.78 times 10 to the negative 5th. This is not good. I don't have anything around me either. Got to finish this. Okay. So I have ammonia. I'm told that ammonia will act like a base. That means ammonia is going to take a hydrogen and give me ammonium. And it's going to leave hydroxide behind. Okay, great. I have a 0.44 molar solution of ammonia. Water is a liquid. I will not consider it, but it had to be present in my equation. Remember, it didn't in the acid one, but it did here because I needed to get that hydrogen from the water. Excuse me, guys. I really apologize for that. Let's just bust in here. 0, 0, minus x plus x plus x. 0.44 minus x, x, x. Kb equals NH4 plus OH negative over NH3. Now, notice it's a Kb. Notice it's a Kb, and I have a Kb, all right? If I had a Ka, I would have to recognize that I need a Kb. Very common mistake. Kb is given to me. Most often I have Ka, and I need to get Kb. Now I'm just plugging in my numbers. I will once again assume to be small. When I do all this math, I will get that X, which is equal to hydroxide, is equal to 2.799 times 10 to the negative 3rd. I need to know the pH, so I'm now going to get the POH because that's equal to the negative log of the hydroxide, which I just calculated, right? That should be below 3, so it should be between 2 and 3, closer to 3. I have it right here. 2.53553. POH equals 2.553. pH equals 14 minus that, 11.45. All right, let's continue on. 5, calculate the Kb of a 0.10 molar solution of a weak base with hydroxide. I would rather go ahead and do number 6 and be done with it, okay? Number 6, I can figure out what we have here. It says Kb equals question mark We have a 0.250 molar. This is turning into a long video, isn't it? Weak base. It's a very important topic in this whole AP Chem universe. All right. All right. So what do I know? I know that if the pH is 9.12, I know 10 raised to the negative pH equals H plus. And I have it down here that that's going to be 7.586 times 10 to the negative 10th. I know that Kw equals H, OH, and therefore OH equals Kw over H. That's 1.0 times 10 to the negative 14th over 7.586 times 10 to the negative 10th. The hydroxide ion concentration must be 1.3 times 10 to the negative 5th. All right, so we have a weak base, whatever it is, it's acting with water. It's probably likely to become more positive over here, right? We have 0.250 molars of it. 0, 0, minus x, plus x, plus x, 0.250 minus x, assume x to be negligible. Kb is what we're looking for. However, x is my hydroxide, right? And that is 1.35 times 10 to the negative 5th. So I know that both of these will be 1.35 times 10 to the negative 5th, right? I didn't have to do all that. Kb equals 1.35 times 10 to the negative 5th. Like, I didn't have to show all that work. I don't think that's necessary. I just wanted you to understand why. Okay. When I do that, guys, I get Kb equals 6.95 times 10 to the negative 10th. Okay. We're going to end that there, and we'll definitely do some practice, get some great FRQs. All right. Thanks, guys.